So let's have this fourth example. Determine whether the sequence converge or diverge. So you have the sequence 1, 1/2, 1 over 2 raised to 2, and then you have 1 over 2 raised to 3, and so on, which a general term is 1 over 2 raised to n. Now, if we are going to replace n by x, so we could have a function, we could have a power function of uh, okay, f of x, which is equal to you have uh, this one. Okay. Now, uh, recall that in your previous calculus, recall that if our b is if our b is greater than 0 but less than 1, then uh, this implies that using the concept of power function, it implies that the b raised to x, okay, will approach to 0 as our x approaches to positive infinity. So in this case, then we could have the limit of you have 1 over 2 raised to n as n approaches to positive infinity. This is equal to 0. Therefore, this sequence is an example of converged sequence because it converged to 0. Okay, so that's the explanation. Now let's have another example. Okay, so you have 1, 2, 2 to 2, 2 to 3, and so on to 2 raised, the general term of 2 raised to n. So again, if we are going to substitute this one, the n by x, then we have another power function. So we could have the f of x is equal to 2 raised to x. Now, from the concept again with the previous calculus that you have, if b is greater than 1, okay, if you have b greater than 1, then we could say that this implies that b raised to x, okay, would be approaching to positive infinity as x approaches to positive infinity. Therefore, if we are going to have the limit of 2 raised to x, 2 raised to n rather, as n approaches to positive infinity, this is actually equal to positive infinity. And if this would be the case, then this is diverge. So the, the sequence is an example of diverge sequence. Okay, so you have shown that the limit of n raised the nth root of n as n approaches to positive infinity is equal to 1. So in this case, we could have, for our solution, we could have the limit of nth root of n as n approaches to positive infinity. Okay, this can be also written as the limit of n raised to 1 over n as n approaches to positive infinity. Okay. Now, using the concept of your previous calculus, using the L'Hopital rules applied to uh, the quantity 1 over x times the natural logarithm of x. So in other words, we can rewrite this one using the concept of the previous calculus that you had. You could have the limit of e, okay, raised to 1 over n times the natural logarithm of n as n approaches to positive infinity, which is, of course, okay, from the previous calculus that you had, if this would be the case, then you could have the limit of this is equal to e raised to 0. And any number raised to 0 is equal to 1. Therefore, we have now shown that the limit of the nth root of n as n approaches to positive infinity is equal to 1. So that would be the explanation there. So sometimes the even numbers and odd number terms of the sequence behave sufficiently differently that is uh, desirable to investigate the convergence separately. So we have the theorem for that. So a sequence converges to a limit L if and only if the sequence of even number terms and the odd number terms both converge to L. Okay. So for example, you have this one. Determine whether the sequence converge or diverge. So you have 1/2, 1/3, 1 over 2 raised to 2, 1 over t raised to 2, and so on. Okay. So here we could separate, okay, the odd and even sequence. So in this case, if we are going to have this one, okay, you could have 1 over 2, 1/2. Then you have 1 over 2 squared. Then you have 1 over 2 cube, and so on. And then you have 1 over 3. Okay. And then 1 over 3 squared. Then you have 1 over 3 cube, and so on. Okay, so the general term here, okay, as we can see here, the general term, you could have 1 over 2 raised to, you could have uh, n minus 1. Okay, and not n minus 1, raised to n rather. And then this one, you could have 1 over 3 raised to n. Okay, and so on, and so on. And then if we are going to get the limit of that, then you have the limit of 1 over 2 raised to n as n approaches to positive infinity. We could have the limit, okay, in this case, clearly we could have here that the limit of these numbers equal to 0. Okay. And here, the limit of 1 over 3 raised to n as n approaches to positive infinity, the limit is also 0. So in this case, we could now say that because the odd numbers and even numbers of the sequence, okay, the odd numbered terms and the odd and the even number terms of the sequence approaches to the same quantity or approaches to the same boundary, then this is an example of converge, because the the odd rather, okay, these are the odd, and the even converges to the same number. Therefore, therefore this sequence is a convergence sequence, or converging sequence rather. So determine whether the sequence converge or diverge. So in this case, as we can see here, the odd number sequence, okay, converge to 1. Okay, as we can see. So as we can see here, 1, 1, 1. So in other words, the odd numbered terms is approaching to 1. However, okay, 1/2, 1/3, 1/4, okay, it is approaching to 0. So since the odd and the even numbered terms, okay, are not converging to a single number, then this is an example of diverge sequence or diverging sequence. Okay, so let's have this one. The squeezing theorem for sequences. Let the three sequences be sequenced such that you have the second sequence is greater than or equal to the first sequence, but it is less than or equal to the third sequence for all values of n beyond the index of n. If the sequence a sub n and c sub n have a common limit of L as n approaches to positive infinity, then the second sequence, the b sub n, also has the limit of L as n approaches to positive infinity. Now, as you can see here in the illustration, so this would be our first sequence and the third sequence. If these two sequence, or if this second sequence lies between these two sequence, if these two sequences, approaching to L as n approaches to positive infinity, it also implies that this sequence is also approaching to the positive, to L as n approaches to positive infinity. Okay, so let's have an example. Use numerical evidence to make a conjecture about the limit of sequence. You have n factorial over n raised to n from 1 to positive infinity, and then confirm that your conjecture is correct. Okay, so since it's stated there that we are going to use the numerical evidence, then we're going to make a table of values. Okay, so you have n, and then we also have n factorial over n raised to n. You can use your calculators. So here, if n is equal to 1, then our first term would be 1 factorial over n, 1 raised to 1 is equal to 1. Okay. And then if n is equal to 2, then you have 2 factorial is equal to 2 over 2 raised to 2 is equal to 4. So 2 divided by 4 is 1/2 or 0.5. And then if n is equal to 3, you can use your calculator. So this would be 3 factorial. 3 raised to 3 now. Okay. So that would be 0.222 and so on. Okay. If it is 4, okay, I am going to use my calculator here. Okay. So you have 0.09375. If it is 5, then you have 0.0384. If it is 6, that is 0.015432098. If it is 7, then you have 0.00611989 98990 and so on. So in this case, okay, clearly we could say that the sequence as n increases, we could say that the sequence approaching to 0. Okay. Now uh, let's try to have the solution, to confirm the conjecture that the limit of this function is equal to 0. So now, if you could notice that if a sub 1, okay, our first term is 1. Our second term is, you have 1 half. And then the third term is equal to 2 over 9, right? Now in this case, 2 over 9, 2 over 9 is less than 1/3. And then you have the fourth term is equal to 3 over 32, which is less than 1/4. Then our fifth term is equal to 24 over 625, which is less than 1 over 5. Then our sixth term is equal to 5 over 324, which is less than 1 over 6. As we can see here, okay, the next terms is actually less than these terms. Okay. In other words, we could have, if if n is greater than 1, then our general sequence would be greater than 1. Then our general sequence would be raised to a sub n is equal to, uh, you have the 1 times 2 times 3 times so on to n over n times n times n times so on, okay, which is equal to 1 over n times 2 times 3 times 4 times 4 raised to n over n times n times n and so on. Okay, for which this follows that a sub n is less than or equal to 1 over n. It follows here. As we can see here, it is less than, they are all less than 1 over n. So it is evident now that our a sub n, okay, is greater than 0. Of course, it's clearly here that it is greater than 0, but less than or equal to, it could be equal to 1 over n. So in this case, okay, the limit of 0, okay, the limit of 0 as n approaches to positive infinity is equal to 0. And the limit, okay, the limit of 1 over n as n approaches to positive infinity is equal to 0. Therefore, we could now say that the limit of n factorial over n raised to n as n approaches to positive infinity is equal to 0 using the concept of squeezing theorem, because the upper bound, okay, here the limit is 0, and then the lower bound also the limit is 0. So in other words, okay, the in between, okay, the in between is also limiting to 0. So that's how our concept of squeezing theorem being applied to. Okay. So let's have this one theorem again. If the limit of the absolute value of n as n approaches to positive infinity is 0, then the limit of a sub n as n approaches to positive infinity is also equal to 0. Okay, so let's have this example. Find the limit of the sequence. So you have 1, negative 1 half, you have uh, 1 over 2 squared, and so on. The general term of negative 1 raised to n, okay, times 1 over 2 raised to n. So in this case, okay, we from the theorem that previously presented, that the limit of the absolute value of a certain sequence, okay, as n approaches to positive infinity, okay, is also the same as if we are going to get the absolute value. So here, if we are going to take the absolute value of each term, okay, for our solution, then we could have 1, 1 half, 2 squared, 1 over 2 cube, and so on. Okay, the absolute value of negative 1 raised to n, 1 over 2 raised to n. Okay, so if this would be the case, then clearly we could now say, okay, this is just the same as, okay, this is just the same as uh, 1, then 1, then you have 1 half, okay, then you have 1 square, 2 squared, 1 over 2 squared rather, then you have 1 over 2 cube, and so on, which has a general term of 1 over 2 raised to n. So in other words, the limit of 1 over 2 raised to n as n approaches to positive infinity is equal to 0. Okay, that is from our previous presentation. Therefore, since this 1 over 2 raised to n is the absolute value is the same with the absolute value of this sequence, then we could now say that the limit of you have the limit of negative 1 raised to n times you have 1 over 2 raised to n as n approaches to positive infinity. So this is just equal to 0 using the concept that we had done in the previous slide. Okay. So in other words, the limit of this function is 0. So let's have sequences defined recursively. So a recursive sequence is a sequence in which the terms are defined using one or more previous terms which are given. So some sequences do not arise from a formula for a general term, but rather from the formula or set of formulas that specify how to generate each term in the sequence from terms that precede it. Okay, so if that would be the case, then uh, that sequence are said to be defined recursively. And the defining formula are called recursion formulas. So let's have an example. Okay, show that the limit of the sequence, okay, this one, okay, you have the first term is 1. However, the next term follows the pattern 1 over 1 half times uh, x sub n plus a over x sub n is 1 square root of 2. Now, if we are going to have the numerical value of this, okay, for our solution, if we are going to use the numerical value, then we could have our first term, okay, our first term is our n here. If our n, and then we have also here x uh, sub n plus 1, which is equal to 1 half times x sub n. plus 2 over x sub n. Okay. If n is 1, clearly it's stated here that the first term is 1. However, if uh, our second term, okay, we could have 1 half times 1 plus 2 over 1, which is equal to, this is 2 to the 3 halves. Okay. And then this is also, if uh, for the third term, okay, we could have this one as 1 half times, uh, you could have 3 halves, okay, plus 2 over 3 halves. Okay. This is this is 6. Okay, 6. So 17 over 6 times 1 half is equal to 17 over 12. And then you have 4. For the fourth term, you could have 1 half. Oh, wrong. I am wrong here. Let me check. Tama pala. So you have 2 times, you have 17 over 12 plus 2 over 17 over 12. So using the calculator, this is equal to, okay, 577 over 408. Okay, and then this for the fifth term, so you have 1 half times 577 over 408 plus 2 over 577 over 408. Using the calculator, this is equal to, okay, this one. Ang laki. Okay, so here we could have say that this is uh, the first term is 1, then you could have 1.5, then here this is 1.4166, so on, and this would be 1.414215, and this would be 1.414235. Okay. So in other words, this is approaching to the square root of 2. What is the value of square root of 2 in decimal? Remember that the square root of 2 is actually 1.412413 562. So still it's also approaching to square root of 2. So therefore, by numerical value, okay, we could say that the limit of this sequence is equal to square root of 2. Now let's try to have another solution. Okay, let's assume that uh, uh, the x sub n approaches to L. Okay, where L is to be determined. And since we know now that n plus 1 approaches to positive infinity as n approaches to positive infinity. Okay, so it is also true, okay, if this would be the case, then it's also true that our x sub n plus 1 would be approaching to L, okay, as n approaches to positive infinity. Therefore, we could have the x sub n plus 1 is equal to 1 half of this one, x sub n, plus 2 over uh, x sub n. There is a typographical error here. This one should be equal to 2. Okay. Okay, let's try to continue. So if this will be the case, we now know that our x sub n plus 1 approaches to L as n approaches to positive infinity. Therefore, we could now replace this one with the limit of this. So the limit of x n sub n plus 1 is L, okay, as n approaches to positive infinity, which is equal to, okay, 1 half times the limit of this one is actually L, right? Okay, plus, okay, 2 over the limit of this is L also. Okay, so you could have uh, distribution. So you could have L is equal to uh, 1 over L plus 2 over 2L. Okay, so you could have L, okay, is equal to, you could have, I have wrong solution here. It should be L over 2. So here we could have L equals, so here you have L that's equal to 2L. This would be L squared plus 2. Okay, so you have uh, so this is 2L squared. That's equal to L squared plus 2. So therefore you have L squared equals 2. Now, the negative portion of this is extraneous. So the negative solution is extraneous solution. Therefore, our L here, the limit should be equal to square root of 2. Therefore, okay, we have now the the limit of the given sequence is equal to square root of 2. Okay, so that's all the presentation for the day. Thank you.